Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 3.2, Systems of Linear Equations. In Chapter 3.2, we start to investigate methods for finding solutions of systems of linear equations. While the theory we cover will apply to larger systems of equations, most of our work will be with systems containing 2, 3, or 4 variables. The first method we will look at will be Gauss-Jordan reduction, also called Gauss-Jordan elimination. We will see that sometimes the given system of linear equations may represent too much, too little, or just the right amount of information to determine the solution. A typical 3x3 system of linear equations, a system with 3 equations and 3 variables, may look something like this. You may recall seeing systems of equations like this in a recent college algebra class or intermediate algebra class. Here, our goal would be to find an ordered triple, XYZ, that satisfy all 3 equations simultaneously. Solutions of 3x3 systems are a little harder to visualize than 2x2 systems of linear equations, but looking at it will help us with an anticipation of what we should be looking for algebraically. Graphically, we are looking for the points of intersection of 3 different planes. There could be no solutions, one solution, or an infinite number of solutions that could satisfy the system. If there are solutions, we would like to describe them. So graphically, the way that we should look at this is that each of these 3 equations individually defines the graph of a plane in 3 space. And these 3 graphs, these 3 planes, could all intersect at a single point. The single point of intersection would be an ordered triple XYZ. This will be what a single solution would look like graphically. Or the 3 planes could intersect along a line. This would provide us with an infinite number of solutions that live along that line. Or the 3 solutions could all intersect on a plane. Now, what this would really mean is that the 3 planes are all actually identically the same plane. They all live right on top of each other. In which case, the intersection would be the entire plane, and we again have an infinite number of solutions. Scenarios where there would be no solution would be when the planes do not all intersect at a single point, or maybe if the 3 planes are parallel planes. Now, we will not be seeking to find the solutions of our systems of equations graphically. However, we will be doing them algebraically. So let's start with our first method, Gauss-Jordan reduction or Gauss-Jordan elimination. Given a linear system of equations, we start by writing the matrix or writing the system as a matrix equation, AX equals B. Recall, to write a system of equations as a matrix equation, we first write our coefficient matrix. This would be the matrix of the coefficients of our initial system, multiplied by a column vector of variables. And this will equal the right-hand side a column vector that was just your digits or your values, your coefficients, not coefficients, your constants on the right-hand side. And we should verify that this is a 3 by 3 matrix times a 3 by 1 matrix. And so that because the inner dimensions agree, we're allowed to do the multiplication. And if we actually did the matrix multiplication, recall that we would take this first row of our coefficient matrix times this column vector of variables, and we would multiply each term as we add them up. So for example, it'd be 1 times x plus 1 times y plus 1 times z. And this would give us our first equation from our system of equations. Now that our system is written as a matrix equation, we will construct what is referred to as the augmented matrix. The augmented matrix is created by taking your coefficient matrix A and adjoining it with your column vector B. Some mathematicians like separating your coefficient matrix and B by this vertical line. Some people do not. It's a stylistic choice. I like it because it breaks off your coefficient matrix from your matrix B so you can see where they're located. But this is a stylistic choice and not something you have to do. We then write the augmented matrix in reduced row echelon form, also called RREF, using elementary row operations to obtain the following. Now, for clarity of the procedure, I have left out the elementary row operations here. However, I will cover them in our next example. But the idea is that you can rewrite your augmented matrix into what is referred to as RREF form. Using our elementary row operations. We then will interpret the RREF matrix and write the solution. So now recall, we'll take this augmented matrix and reinsert your column vector of variables. So this would be your coefficient matrix on the left-hand side, times your vector of variables equals the right-hand side of your augmented matrix. If we were to perform our matrix multiplication, so again, take that first row of A maybe, times that column vector of variables. This would be 1 times x plus 0 times y plus 0 times z equals 1. Of course, all these zeros may not be necessary, so maybe I could write this as just x equals 1, or y equals 4, or z equals -2. This gives us our one unique solution at the ordered triple 1, 4, -2. Now this method, this procedure that I've outlined for you, kind of hinges on the fact that we can rewrite our augmented matrix in this RREF form. It kind of hinges on this step. So let us explore this step a little further. To understand this step, we first need to understand the elementary row operations. So, in step 2 of the Gauss-Jordan reduction example, we omitted the elementary row operations to write the augmented matrix in RREF form. To accomplish this, we need the following elementary row operations. The elementary row operations say that we can interchange any rows I and j. We can rewrite the order of the equations. And notice the notation I'm going to use to represent that. Now, this should make sense why I should be able to do this. If I look back at our original system of equations, what I'm really doing is just changing the order in which I wrote this system of equations. Maybe you're going to write the system of equations as 2x minus 3y minus z equals -8. X plus y plus z equals 3. -x plus 2y plus 2z equals 3. Whoever said that this equation had to be the first equation, and this one had to be the second? The order that you wrote your three equations could have been arbitrary. So we're just changing the order when we switch two rows. Okay. Next, we can multiply any row I by a non-zero constant. And we can add a constant multiple of any row I to any row j. Now these steps that we're performing should seem familiar to you. These are the same types of calculations or manipulations we did when performing the elimination method in chapter 3.1. Okay, let's look at an example. And let's take the augmented matrix from our first system of equations and write this matrix in RREF form. And to give you an idea of what I'm trying to do, again, let's look back. I'm trying to turn this augmented matrix into a matrix that has ones down this main diagonal with zeros above and below the main diagonal. So let's focus on this being our goal. Okay. Now in this example, we already have a 1 in this first diagonal position. I refer to this as the pivot number or the pivot position. And I'm going to use that pivot number to make what's below it turn into zeros. To do that, I look at this number 2, and I want this 2 to turn into a 0. to turn that 2 into a 0 using elementary row operations. And I'm going to use operation number 3 that says I can add a constant multiple of any row to any row. So let's go maybe -2 times row 1 and add that to row 2. Notice how I'm showing my steps here. When we perform this row operation that I've indicated, the first row does not change. So -2 times 1 added to 2 turns this to a 0. -2 times this 1 added to -3 turns to -5. -2 times 1 is -2, added to -1 should be -3. -2 times 3 is -6, added to -8 is -14. Okay. Similarly, we want this -1 to turn into 0. And to do that, using again our pivot number, I'm just going to add rows 1 and 2 together. No, not row 1 and 2, row 1 and row 3. So 1 plus -1 is 0. 1 plus 2 is 3. 1 plus 2 is 3. 3 plus 3 is 6. Okay. Now the next thing I'd like to do, again, I want to get a row of 1s down that main diagonal. I would like this to be a 1. Now how you accomplish this can vary from student to student. As long as everybody is using these same 3 row operations, we will get the same matrix in RREF form at the end. However, the order that you apply these row operations may vary from student to student. The application of this is not unique. However, the end result will be. And what I'm thinking is, I want this -5, I want this number right here to be a 1. I could multiply this row by -1/5, but then I introduce a bunch of fractions. So what I'm going to choose to do is swap these 2 rows. I want to swap rows 2 and row 3. And I'm looking ahead to see what will happen when I do this. If it's not clear, let's swap the rows and then I'll see if I can explain it a little more. If you swap rows 2 and 3, then this now becomes 0, 3, 3, 6, and the third row now becomes 0, -5, -3, and -14. Now, a bit of justification here. Switching these 2 rows like we did should make sense why I should be able to do this. If we scroll back to our original system of equations that we started with, maybe it was arbitrary that we decided to switch these 2 rows. So I'm just changing the order of them. Okay, let's continue. Now that we've switched our 2 rows and I want to turn that 3 into a 1, I can do that by multiplying everything in row 2 times 1/3. Now you may say I'm going to divide by 3. Technically, division by 3 is not one of our row operations. However, multiplying is. So it's an equivalent operation. Now, when doing this row operation, the first row of our matrix will not change. So 1/3 times 0 is still 0. 1/3 times 3 is a 1. 1/3 times 3 is a 1. 1/3 times 6 becomes 2. And the bottom row did not change. Now that we've created a 1 in this pivot position, I want to make what's below this turn into 0. Now I do need what's above it to turn into 0, but generally when I do my work, I do that later. I always focus on making the numbers below the pivots 0 first. Now to turn this -5 into a 0, we're going to go maybe 5 times row 2, add that to row 3. In doing this row operation, the first 2 rows will not change. So 5 times row 2 plus row 3. So 5 times 0 added to 0 is still 0. 5 times 1 added to -5 is 0. 5 times 1 added to -3 is 2. 5 times 2 is 10. Added to -14 is -4. Our next step. Remember, we wanted a bunch of 1s down this main diagonal here. So let's turn this last 2 into a 1. And I'll do this by multiplying everything in row 3 by a half. When I multiply everything in row 3 by a half, the first 2 rows will not change. So a half times 0 is 0. A half times 0 is 0. A half times 2 turns into a 1. A half times -4 turns into -2. Now, at this point, we're about halfway done with our Gauss-Jordan elimination. And at this halfway point, we come up with this matrix that has 1s down the main diagonal. With 0s below the main diagonal. We haven't touched the upper triangular portion yet. But this intermediate step is sometimes referred to as just row echelon form, or REF. Row echelon form has a lot of applications to it. I will not stop here, but just so you can see the application of this step, is that this augmented matrix could be rewritten as a system of equations that would look something like x plus y plus z equals 3, x plus y equals 2. Oh, not x plus y. My bad. Let me fix that. It was y plus z equals 2, or z equals -2. And this RREF form could be used to solve your system of equations. At this step, you could say, well, z has to equal -2. And if z equals -2, you could plug that in, and then you could determine what y is. And if you know y and z, you could plug those in here, and then you could determine what x is. So REF form does have its uses. However, I want to do the complete row reduction technique, the Gauss-Jordan technique. So I'm going to continue now and still write this matrix in RREF form. Remember, in RREF form, I was looking to rewrite this matrix to have ones down the main diagonal, zeros above it, and zeros below it. So I'm going to continue to get the zeros in this upper triangular portion. So let us continue. To get this in the upper or the RREF form, I'm going to use this one now as my pivot and make what's above that pivot turn into zeros. So to do that, I'm going to say, what if we did the negative of row 3 and added that to row 2. And now I'll turn this into a 0. Now in doing this row operation, that bottom row is not going to change. So it's still going to have 0, 0, 1, negative 2. But when you go negative of row 3, you'll do negative of this, added to this, that's still 0. Negative of this, added to this, is still 1. Negative of this, added to this, is now 0. The negative of this would be positive 2, added to this is now 4. Now I also need this entry to be a 0, so we'll do the same thing. Go negative of row 3 added to row 1. So negative 0 added to 1 is still 1. Negative of 0 added to 1 is still 1. Negative of 1 added to this 1 becomes 0. Negative of this negative 2 is now positive 2. Added to 3 becomes 5. Notice we're almost done. But already I can tell you from this line, z has to be negative 2. And from this line, y has to be 4. Okay, but to finish off, again, I want to have only zeros above the main diagonal. So I need to turn everything up here into zeros. I need that one to be a 0 there. To accomplish this, I'm going to use this 1. I'm going to call this my pivot number and use that to make everything above that turn into 0. So what if we did negative of row 2 and added that to row 1? In doing this row operation, the bottom row will not change. Well, the bottom 2 rows are not going to change. So let's copy the bottom 2 rows down. I think if we went negative of row 2 plus row 1, it would be negative of this 0 added to 1 is still 1. Negative of this 1 is negative 1. Added to that 1 is 0. Negative of 0 added to 0 is still 0. Negative of this 4 added to 5 is 1. And this finished our steps because we now have the augmented matrix in reduced row echelon form. And because it's an RREF, we would be able to finish finding the solutions of our system of equations by identifying that this can be rewritten to say x is equal to 1, y is equal to 4, and z is equal to -2, which is the ordered triple that is our solution that we found in our first example. Now, I'd like to continue on. What I have not done in our lecture today is actually define what it means to be in RREF form. I haven't actually defined this. I just said in our previous example that we're in RREF form when we look like this, but I haven't actually defined what that means yet. So let's look at that in our next page. Okay, so what is reduced row echelon form of a matrix? Also referred to as RREF. A matrix is in reduced row echelon form if it satisfies the following conditions. If there is a row of zeros, it should always be at the bottom of your matrix. Such as this example, you see the third one down here has a row of zeros at the bottom. The leftmost non-zero entry of each non-zero row equals a 1. And from the example we started with, again, this is our typical matrix in RREF. The leftmost entry of each non-zero row is a 1. It's like if this were a 2, that would be a problem. The leftmost entry always has to be a 1. This entry is called its pivot or leading one. Each pivot is further to the right than the pivot in the row above it. So when you think about pivots, here's a pivot. The next pivot is down and to the right. The next pivot is down and to the right. It does not have to be immediately to the right. It can skip a couple of values, but it always has to be down and to the right. For example, if this were a 1, I would be fine with it being down and 2 to the right. It's not a 1. It's a 2, so I have a problem there. But if it were a 1, I'd be okay with that. Just be down and to the right in some way. And then lastly, each pivot is the only non-zero entry in the column. Each pivot is the only non-zero entry in the column. So let's look at this exercise. In this exercise, we're asking which of the following matrices is in RREF form and which of the matrices is in just REF form. So remember, REF form is one in which we loosen the requirement that each pivot is the only non-zero entry in its column. In our last example, I had made a point when I had made it to REF form. If I scroll back for a moment so you can see that, then we can say this matrix here is a matrix that's in REF form. It's an REF because these values are not 0 yet. You only have 1s down the main diagonal and 0s below it. But since they're not 0 above it, that makes this REF form. So here we go. I'd like to identify which of these matrices is in REF, which of these matrices is in RREF, and if a matrix is not in one of these two forms, identify which property is being failed. So here we go. First one. So I'm going to say each pivot is down and to the right of the pivot above it. There's only zeros in those pivot columns. Each pivot is the leftmost non-zero entry. This one I want to say is RREF. This one, also RREF. Remember, if there's a row of zeros, the zeros have to be at the bottom. Each pivot is down and to the right from the pivot above it. Each pivot is the only non-zero entry in that column. Third one. The third one is neither. REF or RREF. And the reason it's neither is because this value of 2. That 2 would have to be a 1 in order to be an RREF. Because then it would be every pivot is down and to the right of the pivot above it. Every pivot is the leftmost entry. Every pivot is the only non-zero entry in the column. It's neither, though, because the value in the second row, third column, in the 2, 3 position. That's why it's not an RREF. Otherwise, I'm okay with this. Okay. This one, is this an RREF? Now what I'm looking at is this is the coefficient matrix A. Remember, the things on the right-hand side is the B. Don't look at that. In this problem, we're only looking at the coefficient matrix A here. Only looking at the coefficient matrix. So I would say this one is an R. Oh, it's not. Nope, because here's a pivot. The only thing in that column has to be zeros other than that pivot. That 2 is the issue. If this is a pivot, you're supposed to have only zeros other than that pivot in that column. So I'm going to say also neither. Because of the value in the first row, second column, so in the 1, 2 position. That 2 would have to be a 0. Okay, this one. Again, we're only looking at the coefficient matrix here. I would say this one is in RREF. Again, just look at the coefficient matrix. It's not in RREF because of the values above the pivots. But I would say this one is in REF. And this last one, also in RREF. Okay, so remember, we're going to be using this elementary row operations to try and get our matrices to be in RREF form. There's different ways it could look, but we're trying to make it look like this one, this one, this one, or this one, for example. This is our goal, is try to get them in these forms. Now, there's still more that can be done, though, because once your matrix is in RREF form, we want to be able to talk about the existence and the uniqueness of solutions. Meaning, does a solution exist? And if it does exist, is it unique? Is there one or more solutions that exist? And we can get that from the RREF matrix. So to do this, let's talk about the rank. The rank of a matrix is the number of pivot columns or the number of pivots that it has. It's the number of ones that we have down that diagonal. If the rank of a matrix, written as R of A, rank of the matrix A, satisfies the following. If the rank of your matrix is equal to the number of columns, then there is one unique solution. And I should specify here, it's the number of columns in the coefficient matrix. I did say A, but let's make sure we say it's the coefficient matrix. If the rank of A is the same as the number of columns in the coefficient matrix, then there's one unique solution. If the rank of A is less the number of columns in the coefficient matrix, then there are infinite numbers of solutions. And the way we represent our infinite numbers of solutions is by finding your homogeneous solution and adding it to your particular solution. And of course, I'm going to do that in some examples with you today. If ever you have a row of zeros in if ever in your RREF matrix you see a row that looks like this, it means that there are zero solutions. And the reason why you want to see is because this augmented matrix, if I rewrote it at a system, it might look something like 0x plus 0y plus ... 0z equals 5. Now I'm letting k be the number 5. It would mean there's no solutions, because how could you have 0 of this and 0 of that and 0 of that equals 5? That doesn't make sense. A bunch of zeros does not equal 5. That's what tells you there are 0 solutions. So let's look back at our previous example and identify the existence and the uniqueness of solutions. So here we're in row reduced form, and you want to say here that the rank is 3, which matches the 3 columns of our coefficient matrix. This one has one solution. The second one. Here the rank of A is, you want to say how many pivots there are, how many ones are down that diagonal. Rank of A is 2, which is less than 3 because there are 3 columns in the coefficient matrix A. This one has infinite solutions. I do need to show you how to find those infinite solutions, but I can tell you that one has infinite solutions. This one. Now this one's not even in RREF form, but I hope you could imagine that you could write this in RREF. You could do more steps. You could write this, in which case this would be a 1 eventually. So it's not in RREF yet, but if you wrote it in RREF, this would be a 1, and you would be able to say that the rank of A would then be 2, because this would be a pivot. This could eventually be a pivot, and this is less than 1, 2, 3, 4, 5. There are 5 columns in the matrix A. This one would have infinite solutions as well. This one. Here I'm noticing the bottom row. this again tells me something like 0x plus 0y equals 1, which tells me that there are no solutions here. This one. This is in RREF form. Notice that there is 2 pivots, so the rank of A is 2. But there are 4 columns in the coefficient matrix A. This one's going to have infinite solutions. This one's in REF form. I could get it into RREF probably, but I think what you want to know here is that the rank of A, how many pivots there are, is 3, but there are 4 columns in the coefficient matrix A. This one's going to again have infinite solutions. So if you're comparing here, you're only going to have one solution. Another way to see it is if your coefficient matrix turns into the identity matrix. If this looks like the identity matrix, that's how you know you're going to have one solution. But if it's some other variation, that's how you know you're going to have infinite solutions. Okay, this last one, I'm looking at the bottom row here. Notice how it's 0, 0, 0, 0, 0, 2. This result tells me this will have no solutions. Okay, there's a lot going on here, but I hope this gives you an idea how to think about a matrix, how to determine if there's a solution, and how to find the solution. I'd like to do a couple more examples with you, but this video is getting to be about 47 minutes long, so I'm going to stop this video, and I'm going to do the remainder of the examples in another video. I think there are 3 more examples in this set of guided lecture notes, and so I'll see you in the next video, and I'll do those last 3 examples. I hope this is helpful, and I'll see you then.